Okay. So we had some interesting properties of harmonic functions. So there was maybe a theorem that was left as an exercise. I think that was the closure property. Closure property of harmonic functions. I think that you should. Did you try to do this this theorem? Maybe it's not so easy. Eh? So let UH be a sequence of harmonic functions, classical harmonic functions. You see harmonic functions, C2 functions in omega open, the open set omega, and suppose that UH converges to U uniformly on compact subsets. Then U is harmonic. I think that this was one of the exercises, right? So did you try to prove this? Did you try to prove this theorem? Do you succeed?
Maybe.
Maybe.
Just take a ball, compute the difference between UX and an average.
Yes, this could be an idea. So we know, so since U is harmonic, first of all, okay, since U is harmonic,
you mean the sequence? You mean the sequence?
Since UH is harmonic, yes. For any x in omega and rho, for any rho, say in 0, the distance between x and the complement of omega, we know that UH satisfies the volume mean value formula. So we know that this is equal to omega n rho to the n integral 0x UH of 1. Observe that UH, these are harmonic, so we know we proved last time that UH is actually in C infinity, not only in C2, but is actually much more, is in C infinity, no? And in particular is continuous, and UH converges uniformly on compact subset, therefore U itself is continuous, because it's uniform limit on compact subsets. So UH is U uniformly, sorry, locally uniformly in omega implies that at least U, we don't know its smoothness at the moment, but this is at least continuous. We can also pass to the limit here as h goes to plus infinity in this equality for fixed rho, if you fix rho for any x in omega, such that when you fix x, you fix rho such that you have this, then you can say that surely this converges to u of x, because we have local uniform convergence, so in particular we have pointwise convergence. And also we can pass to the limit inside the integral sign. So this surely converges to 1 over omega n rho to the n integral dx dy dy. So by uniqueness of limit we have this. So what we know about u, so about u we know about the limit u, the limit function u, for the moment we know that u is continuous and u satisfies the volume mean value formula, where this v means exactly, by definition, if you remember, is this. Okay. Now let us multiply both sides by this denominator. Okay, so we have omega n rho to the n u of x equal to integral u rho x u of y dy. This is true given x, is true for any rho inside this interval. So we can differentiate this equality in rho and we get, so differentiating with respect to rho, is, so n omega n rho to the n minus 1 equal the derivative of that. But I think that we know what is this derivative with respect to rho. No? Do you remember that we made this computation? You will find in your notes, surely. And this has been done. If you look carefully in your notes, this has been done. The idea was...
We changed the unit units.
Yes, the idea was to take the quotient, the incremental quotient, so you are integrating on an annulus, but you are dividing by the height of the annulus, and when you let h, which is the height, to 0, it turns out that your integral is just evaluated on the boundary. Do you agree? You remember this? Okay, so this... So I don't remember the lecture, but it is in one of the previous lecture. One of the previous. So this coincides actually with your y, the h n minus 1 of y. And here I'm using, it's an important remark that u is already continuous. Because if it is already continuous, we can integrate it on a set of zero Lebesgue measure. So I mean, it is pointwise everywhere defined, and so I can give a meaning to u of y for any y in this hypersurface. So there is no ambiguity in this definition. So from the volume in very formal now we sorry, here there is something missing, u of x. So now we divide, this is sigma n minus 1. Remember one of the previous exercise that we made. So now we divide by sigma n minus 1 rho n to the n minus 1 to get that u of x is 1 over sigma n minus 1 rho to the n minus 1 integral of the boundary of the rho u of y dh n minus 1 of y, which is, by the way, nothing but the so we have shown that as soon as u is continuous and as soon as u satisfies the volume mean value formula, then it satisfies also the surface mean value formula. Do you agree? So we have proven a sub-exercise. U continuous, U satisfies volume mean value formula, implies U satisfies. No, so this is maybe a remark. Used in this proof. Why we use this? Because now you remember last time we have shown that if we have a continuous function which satisfies the surface mean value formula, then it is C infinity. So from last lecture, regularity result, C infinity regularity last lecture, we get that this was based on the use of convolutions. So if you remember, we proved that u star by epsilon actually was equal to u in a smaller in omega. So we know now that u is C infinity. Okay. In particular, so, summarizing, for the moment, we have something more. For the moment, up to here, we have that for u, we know that u is C infinity, and satisfies volume and surface mean value formulas. Okay, which is something more. So let's go back to this. I think that we have shown we have this equality, and we have shown one of the previous lectures. We are able to compute. So let us call this f of rho. I think that in one of the previous lectures, now I don't remember which lecture, we showed that f was differentiable, and we computed also f prime. So f is differentiable. This was one of the previous lectures. One of the previous lecture. And f prime of rho, are you able to find which was the idea? Was to, because the problem was that we have rho also here, no? Yes. but we can rescale to the ball of radius 1, to the surface of the ball of radius 1, and rho goes inside. So there is no anymore, if you rescale, y is in the ball of is here, no? So if you call z equal y divided by rho, then z is in the ball of radius, is in the boundary of the ball. So you do this kind of trick to rescale it, but this we have already done. And we compute, and we are able now, the dependence on rho is just only inside u, because this becomes the integral over the surface of the boundary radius 1. Now do you remember?
Yes.
So I think that this was integral u of rho z. No? And now we see from here that this is differential with respect to rho, and we can do the differential. So, and we found that this was, we computed the derivative, and the derivative now will scale back to the old ball, and this I think becomes 1 over sigma n minus 1 rho to the n minus 1 integral b rho x du over the nu b rho x. Can you check? Did you find it? I don't remember which.
We assume that it should be at the origin, the one we did.
Okay, it's the same. But the result, we made this for x equal the origin, but this is the result. Hmm? Do you recognize it?
Yes.
Okay. Now we use the Gauss-Green theorem here. So you should be able to tell me now what happens is this factor correct?
Which one was in mind?
Okay, you should raise to power n.
Eh?
I think you should raise to power n.
Well, we could do the derivative,
I think we should raise to power n.
because this is equal to this, no? So when we differentiate with respect to rho, this is equal to the boundary of the 1 of x into rho z, scalar z. Okay, and then we go back to the dh(n-1) z, and then we go back to this change of variables. So y equals rho z. So we want to check if this power is correct or not.
It is correct.
It is correct? It is correct. Huh? It is correct. Rho to the n-1.
I think there is a root to the n-1.
Okay, it's correct. Okay. So what do we get? So we do the Actually, I think that we even don't need to. Okay, doesn't matter. So we do the Gauss-Green and the divergence theorem, and we end up with this, no? Remember, the divergence of the gradient of u is equal to grad u scalar mu a. Okay. So I apply this theorem when A is the ball of radius O. But this is equal to 0, this derivative, because this is u of x as independent of rho. I am differentiating with respect to rho. So what do I find? I find that this is equal to 0. So for every rho, exactly. So what do I find? I find that for any x in omega, for any rho 0 to omega x, I found that the integral, we know that u is infinity, in particular it is C2, so this is well defined, and we found that this is equal to 0 is equal to this. So now I can divide this by, I can take 0 is equal to, and then I can let rho to 0 plus. So I have a continuous function. The limit as rho goes to 0 plus to this quantity must be 0. But the limit is the value of the continuous function at the center by continuity. Because we know already that it is C2, it is infinity, which is the relevant part. So letting. So as you see, this is not really an exercise. This may be a theorem. Letting rho to 0 plus here, since Laplace of u is continuous at x, we get 0 equal plus of u, which shows that u is harmonic. No? So,
maybe I missed something, sir. From this integral, we have 1 over sigma n minus 1 to n minus 1.
I pass the volume integral.
Okay, from volume integral.
Then I forget about this, doesn't matter this. If I pass the volume integral, I know that this is 0.
This is 0.
Now I divide by the volume.
Okay.
So I take the mean value, volume mean value. So we have this important closure property of harmonic function. As soon as I take a limit of a sequence of harmonic functions in this topology, I know that the limit itself must be harmonic. So I don't escape out, I don't go out from the class of harmonic function when I take this limit. Even if harmonicity is defined through second derivatives in some sense, and I have the convergence only on u and not any kind of convergence on the gradients, still I have this property here. So the topology is rather, the convergence is rather weak with respect to the operator. The operator involves two derivatives. Instead, the convergence involves zero derivatives. So it's somehow surprising that for an object which satisfies a PDE of second order, I have a sequence of objects satisfying a PDE of second order, but the convergence is taking only in C0, still the limit satisfying the second order PDE. It's non-trivial, this fact, this closure property.
Can we extend this property more than uniformly, like maybe monotonic?
Yes, it can be extended to a different topology. This requires some work to do. Maybe we will do this extension, but not today. So remember, the class of harmonic functions is closed under this kind of convergence. Then there was another, I think that I gave you some other exercise. I think yes, it was this one. Improved convergence, let me call it. Improved convergence. So let UH be a sequence of harmonic function in omega open. Suppose that UH, like before, converges to U uniformly on compact subsets. Then for any multi-index, alpha, for any omega prime open set, say with compact with closure, say omega prime is compact, the closure of omega prime is contained in omega. This means the following. Maybe I need also omega prime compact. We have that the supremum by the way, from the previous closure theorem, U is harmonic. Okay, so it is smooth. This also converges to zero. Sup tend to zero as H. So what I want to say is, namely, grad alpha U H converges to grad alpha U uniform and compact subset of omega for any multi-index. On compact subsets. So if you want, you can remove from the statement this part, because this is exactly the same as this. I'm saying the same thing. Again, surprising, no? Because in general, when you have a sequence of functions converging uniformly to zero, say, there is no hope to gain any convergence on the derivative. You go to zero, oscillating a lot, so that the derivative does what it wants. Okay, so there is no, but these are harmonic. Okay. So did you try to prove this? This was one of the exercises. Well, I think that this is a really direct.
It follows from the because also these are harmonic.
No, it follows from the gradient estimate. You remember last time we made a difficult, crucial central result, which was, let me write it here. So for any alpha, I think that we have this less than or equal. Then we have the L infinity norm on a ball, say, sup over u, say on some ball. No? Sup of u maybe yes. Hmm? But omega, I think this supremum could be plus infinity. Okay. If it is plus infinity, the estimate is trivial.
Yeah, it's true.
So okay, sup. Then there was important constant thing. There was, so suppose that yes, the length of this multi-index was k. Then we have this to be k, and then we have the dimension. It was this, right? This precise. No? So you see, now you see u is harmonic in omega by the previous theorem. By the previous theorem. Therefore, UH minus U is harmonic. Hence, for any H, UH minus U is harmonic in omega. So we can apply to UH minus U this estimate. So and we have, so if you fix omega prime, from this estimate it's not difficult to see that you have grad alpha UH minus U at a supremum. Less than or equal than some constant. Then you have the distance between omega prime and the complement of omega. To the power k. And you have here alpha is equal to k. Where C is the supremum of U on omega. Okay? If it is plus infinity, it's okay.
But the supremum of U, H minus C.
Oh, yes, yes.
You want to make to infinity.
If you want, I write it. And now you see, k is fixed. So n is the dimension, k is fixed, this is a number because omega prime is fixed. Everything is a number and h goes to infinity and this goes to 0 because UH is converging to U uniformly in omega prime. So this goes to 0 and therefore also this one goes to 0. So improved convergence, from just the convergence in uniform convergence, you get the uniform convergence of all derivatives. Again, another important result. And finally, there is a third result in this spirit, which we could call compactness result. Compactness result. So the theorem let UH a sequence of harmonic functions locally uniformly bounded in omega. Then there exists a subsequence, so let me denote it, but no, I don't denote it, subsequence of UH and a harmonic function U harmonic in omega, such that UH converges to U uniformly on compact subset, such that local uniformly and for any multi-index grad alpha locally uniform. In omega. So do you have some suggestion for this kind of theorem? Yes, exactly. Exactly.
There is a subsequence.
Yes, yes. So what does it mean, locally uniformly bounded? So you fix omega prime as before, a compact in open set, compact closure contained in omega. So what does it mean? It means that you do the supremum of UH of x and sup of x, sup over x in omega prime, and this is uniformly, this is bounded. So sup, this means okay. This means, so you fix a compact open, an open set with compact closure. You look the supremum of UH there, and then you take the supremum over H, and this must be a bounded. This must be a bounded sequence. Okay. As he was saying, I think it's correct. So what do I do is simply that now I look. So the sequence UH, the restriction of UH on omega prime now is uniformly bounded, uniformly bounded. And also it is uniformly, equi-uniformly continuous, because the gradient of UH is bounded by a constant, depending on the dimension, whatever, times the sup of UH itself. So the gradient estimate implies is equi-bounded. Equi means with respect to H, so no, equi-bounded and equi-Lipschitz. So in particular, equi-uniformly continuous. No? What I mean is that the supremum over H of the supremum and the gradient of UH is bounded. There is a uniform bound for all these objects with respect to H. It is uniform. I can take a number bounding this independent of H. I can take another number bounding this independently of H. So there exists a number such that this is less than or equal than this number for any H. And there exists another number such that this is less than that number for any H. So, and the H is independent, and this number is independent of H. This means this word equi. Is this clear? Equi means uniform with respect to the index.
The super here is over omega prime.
Thank you. Thank you. Omega prime. Ascoli Arzelà, the main compactness theorem in this omega prime, in the closure of omega prime. So this says that there exists a subsequence UHK, and there exists a function u defined in omega prime such that this converges to some function u in omega prime uniformly in omega prime. So what do we know about u? U is defined in omega prime and is harmonic, and is harmonic in omega prime by the previous result. And also we have this estimate by the improved convergence result that we proved 5 minutes ago. So this for the moment holds in omega prime. Now it's sufficient to take a sequence of open sets omega prime with this property, compact, the closure is compact contained in omega, take a sequence and then for any of each element of the sequence of omega prime you have a subsequence, and then you extract by diagonal procedure a countable number of subsequences if necessary to get the convergence in omega. So now invade omega with omega prime I contained in omega prime I plus 1. And do this reasoning for any I, and do a diagonal argument. Make the above argument on each omega I, and use a diagonal argument to extract a subsequence. So maybe yes. So we extract a subsequence k depends on I, but I is countable. So the argument to extract the required subsequence and to get So summarizing, we have so this gradient estimate is really crucial. To have essentially all this compactness and this improved convergence. Okay, now maybe let me see in the program that there is this. Before doing, we have not yet concluded the regularity part because we don't have proven analyticity, unfortunately. So analyticity, we are in infinity, but we don't know that harmonic functions are real analytic. This we will do later, but first we do something that we don't need, for which we don't need analyticity. And this is called the strong maximum principle for classical subharmonic functions. Remember what we have studied about the maximum principle. First of all, maximum principle is related to subsolutions. Do you remember? On the other hand, minimum principle is related to supersolutions. And therefore, for a solution, we have maximum and minimum principles. Good. Subsolution in one dimension means convex. And the weak maximum principle that we have studied was saying, compatible with this picture, that the supremum of this object in omega is equal to the supremum of this object on the boundary of omega, but there was an assumption on omega. You remember the assumption? Omega, open? Yes, omega is always open in this discussion, but it was bounded. Okay, and because otherwise, if it is not bounded, we had the counterexample. So that was relevant. Okay, but that was not excluding the presence of interior. So that was called weak exactly because it does not exclude the presence of interior maximum points. If you have a constant function, this is subharmonic. All points of omega are maximum points. So at that level, we were not able to exclude the interior maxima. But now we want to exclude interior maxima. So now we make another kind of assumption on omega. So let omega be connected. And suppose that u is non-constant. Let u be omega, and suppose it is non-constant. Okay.
Omega is not necessarily bounded.
No. And then you cannot have interior maximum point. You cannot have interior maximum. You cannot have maximum point in omega. Okay. Not have maximum point. What do you think about this? Do you have some idea?
What do you mean?
Yes, I think that we could try to use the volume mean value formula.
We can suppose that
Okay, so suppose, so if the supremum of u, say, is plus infinity, in order, then I think that surely there is no interior maximum point. No? Because u is infinity, yeah? It's the UC2. Sorry, u is C2. No? So there is so we can assume sub u is So suppose by contradiction, so let me call this number finite capital M. Okay, now suppose by contradiction yes, you will see that I will not use any kind of boundedness in this proof. On the other hand, if you remember the proof of the weak maximum principle, we use it in the proof. So suppose by contradiction there exists one point where u is maximum. So now what would you do? Yes, the idea is, well, we still have to use connectedness, remember. So we have to contradict something. So the idea is to define two subsets. Sorry. This set here and this set here. So we will reach a contradiction if we show. First of all, it is clear that A union B is omega. And it is also clear that A intersection B is empty. So we will reach a contradiction if we show that both A and B are open and not empty. So we will have a contradiction if we show that A, B are non-empty and open. Now, what about B? Can we say that B is open? B is open. Why? Because U is continuous. You see too. So B is open. Can we say that B is non-empty?
Because U is not constant, it should not be empty.
Exactly. Since by assumption, U is not constant, we have that B cannot be empty. For B, we are okay. Now let's see the main point on A. Can we say that A is non-empty?
Because we pick a choice, it's not.
X naught is in A by our contradictory assumption, no? So A is non-empty. So it remains to show that A is open. It remains to show that A is. Do you have some idea to show this? So we should have to find a neighborhood of all.
No, we need to use volume.
No, so we know that, so take rho in 0, x naught, and we know that u of x is less than or equal to, because this is a subarray. Exactly. We go to the n, integral b rho x naught, p of y dy. So, now you see, sorry, u of x naught, this is equal to n. Let's look at this inequality. And x naught is a maximum point, right? So this means that the values of u in a neighborhood of x naught are less than or equal . Because m is a maximum point. So how can this be possible? This u is continuous. So the only possibility is that this must be an equality. Otherwise we reach a contradiction.
Yes.
Because this is a continuous. If it is smaller than in some part, then this inequality becomes false. No? So since u is continuous, in order not to contradict in order not to contradict this inequality, we must have u of y equal m and y 0 x naught. But this means, if you remember the definition of A, this means that the ball below x naught is all contained in A. So as soon as x naught is in A, we have a ball inside. which shows that x0 is an interior point. X0. Or in other words, that all points of A are interior. All points of A are interior, which means that A is open. Okay? So, now finally we use the connectedness, because we have split omega into two disjoint open and empty subsets. So omega cannot be connected. Okay? Contradiction. Because omega is connected. Okay. Is this clear up to now? Okay, perfect. Clearly, as a corollary, if you have a harmonic function, non-constant harmonic function on a connected open set cannot have interior maxima and minima. Because it is at the same time a sub-solution in the super-solution. Okay. Maybe before doing the analytic, I would like to tell you this result. Okay. Here. So let us do this. However, this theorem we do this for harmonic functions, not for subharmonic. We do this really for harmonic. So let omega be open. Okay, open is always the case, but connected. Unconnected. And suppose that U is harmonic in omega and non-constant, harmonic in omega and not constant. Then U cannot have interior. This is much stronger, local maxima, and cannot have interior local maxima, and cannot have, okay, interior local minima. So before, in the case of subharmonic, we have excluded global interior maxima. But how to exclude local interior? Instead the global, now local. No? Let's see. Interior local minima.
If U has some
Okay, suppose x naught is an interior local maximum. Is a local interior local maximum. So what does it mean? It means that there is a small ball, small or large, I mean there is a ball. X naught, such that you restricted to the ball. If I look at the restriction, this is harmonic and has a global. It's harmonic and has a global. So let me call this B maybe. This restriction. So B is harmonic and x naught is a global max. Is a maximum. Is an interior maximum. No? So now we want to apply the previous theorem to the new function v and to the new open set below. So let me call this let me call this the new domain, the new function. Open connected, yes. This is open connected. So can we exclude that? Can we exclude this situation? Can we apply the previous theorem?
Yes. So only
Be
case
careful.
just v is constant. Only case, its only possibility is just v constant, should be constant.
How can we exclude this?
If v is not constant, so we know.
I mean,
the difference.
In order to apply, what I want to say is the following. I want to apply the previous theorem, but in the previous theorem, besides the connectedness of the domain, there was also that u was non-constant. So, and we don't know that the restriction of v. In principle, how can we say that we need, in order to apply, the previous was called the strong maximum principle. Previous. Did I write it strong? Okay. In order to apply the strong maximum principle to V, we have to check a missing assumption, because we know that U is non-constant, but we are looking at an enabled. In principle, there the restriction of U could be constant. Why not? No? So we have to check that V is non-constant. And at this level of our knowledge, we cannot exclude this situation. I don't have, seems to me at the moment, I don't have any way to exclude this. So I need a further result, which is analyticity. We shall prove that U is analytic. That any harmonic function is not only C infinity, but also real analytic. And therefore, V is also real analytic. Hence, V is analytic. But now, V is analytic. But now, if I have, by the identity principle for analytic functions. How is it called? Two analytic functions cannot coincide on an open set unless they are equal. See, no? I mean, if you have two analytic, analyticity is very rigid. If you have two analytic functions,
it's the uniqueness property.
Uniqueness continuation property, maybe. Yeah. Uniqueness continuation. So if you have two analytic functions that coincide, say, on an open set, they must be equal. They cannot separate anymore. Okay. So, if V is constant, this means that U is constant on an open set. But if U is constant on an open set and U is analytic, U must be constant. Which contradicts this assumption that up to now we have not used. So U is constant in VR, and U must be constant in the connected component. Must be constant in the omega is connected, so must be constant in the connected component containing x naught. U must be constant in omega, which is a contradiction. With this. So this is more refined. Evidently, this kind of maximum minimum principle is more refined. And you see, I did this for solutions, not for sub-solution or super-solution, because solutions, I know they are analytic. I will prove they are analytic. Okay, so now, if this is clear, we can go to the regularity analyticity. Okay, so this is delicate. As I said, we can somehow, the fact that this should be analytic is understandable. So theorem. Why it should be understandable? Let me first state the theorem and then we try to imagine why this should be true. So theorem, let U be harmonic in omega open, then U is analytic. Why this should be true? Again, because the crucial gradient estimate, grad alpha u of x less than or equal than some constant depending on the supremum. Then we have e omega x, okay, alpha, okay, and k, supremum of u in both, say. Because the idea is that I need to consider the Taylor expansion.
convergence.
And I need to show that the remainder of a Taylor expansion in a suitable ball, sufficiently small ball, say, uniformly converges to zero. This is the Q, or the Lagrange remainder. Let's see, now we will say, I will be more precise. And once I have this, factor here, somehow analytic functions, once you have sort of control of the gradient of the various derivatives, these are inside the coefficients of the Taylor expansion. So once you are able to control this in terms of a suitable object, you can imagine to try to find a series, numerical series, independent of x, in a small ball, which is converging. And therefore, I mean, you can say that this, from this bound, from this object, let's say, from this fact, I mean, maybe there is a way to show. So the fact that you have a bound on the gradient of this sort is somehow indicating that maybe you can have convergence to analytic function. So to make this rigorous, I need some notation. So let's do, first of all, let's fix for simplicity x equals 0 and suppose that 0 is in omega. Okay. So we fix the by possibly translating, we suppose this. Okay, this is one assumption. Next, I need to introduce d. For simplicity, is this factor here. We call this d. And then we want to show that u of x in a small ball, say b of radius r, centered at 0, and say that r is, take r, say just here. So the situation is the following. We have, this is omega, this is 0, then we have the distance, this is d, then we take d half and say, consider stable sort. So we need to show that this coincides with the Taylor expansion. Now I need to tell you the notation. Sorry. So I think that you know, now we know. So alpha, so if alpha is a multi-index, the length of the index is alpha 1. So if alpha is a multi-index, alpha is equal to alpha 1, alpha n. Then the length is the alpha 1 plus alpha n. The alpha factorial is alpha 1 times alpha n factorial. X alpha by notation is, so x is x1 xn. And the definition, x alpha is this. Okay.
Why is this factorial is 2?
2.
Is this factorial equality?
Now this is a definition. this is the definition, yes, definition. This is the definition. This is the definition. And what does it mean, this? This we know, I think. One. The alpha, sorry. U. And this, together with this, means this times this. Okay. I think this, I hope that this is the just product of numbers.
This is x1 to the alpha over.
Sorry. X1 is thank you. Sorry.
And this also in
X alpha. Or it's just
x1.
X1.
What I'm saying is in this graph, I'm not going to have multiple of x alpha. So I have this x alpha 1.
Sorry?
This last equation.
Yes, this
Are
one.
we not supposed to have x alpha here?
X alpha.
That gives this x alpha, x1 alpha 1 up to xn alpha.
Yes, this is a definition again.
Yes. I think the grad of alpha u of 0 is
yes, multiplied by the x alpha. Thank you. Sorry. This is. Okay, this should be the notation. And we have to show, so ux is given. We have to show, therefore, that this series is converging to ux. And so they coincide. So this now, I don't know, probably there will be definitely today no time to do this proof, but let me write at least what we want to show. So let me write the Taylor expansion up to some order with the Lagrange remainder. Okay, so I fix an order, say k. So ux minus. Actually, I think this probably is from the sum from 1, right? Oh no, because you have u of 0, yes. Minus u of 0 minus sum alpha equal 1 grad alpha u of 0 x alpha minus sum alpha equal k minus 1 grad alpha u of 0 x alpha. This is there is an intermediate point that I denoted by xi. Okay, grad alpha u of psi x alpha over alpha factorial. This is just the Taylor series for some psi. So we are x is inside this ball, so psi is again inside this ball. Is in between x and 0, so it is again inside the ball. So, and remember that F is less than u over 2. Just. So we have to show that this object here, which is the Lagrange remainder of order k, Lagrange remainder. So we have to show that this Lagrange remainder converge uniformly to 0, yes. Because this psi depends on x. But we have to bound this uniformly. This is Taylor formula.
No, it's still bound the grading.
What do you mean?
Still?
No, I don't use Stirling formula. No.
No, this is Lagrange.
This is just the Taylor formula with the Lagrange remainder. The difficulty here is that the presence of the multi-index formalism, which makes things a little bit confusing.
For this we know we have gradient estimate, but I think we need to calculate this alpha. We need to calculate the number of which this.
We need to use the gradient estimate, and then we have to be very careful. So the problem is show. So we have to show what we have to show. We have to show that the Lagrange remainder converge to 0 uniformly as k as k goes to plus infinity. This is essentially what we have to show in order to prove analyticity. Okay? This is what we have to show. And then we have to use, of course, the gradient estimate, but not in a trivial way, I think. I mean, yes, there will be some induction, it requires half an hour. At least more or less half an hour, 25 minutes to show this. So I propose to postpone this to tomorrow. It's time. Okay? So let me see if I can give you. So I would like that you, I don't know if you try to do the exercise of, I would like to leave you, maybe I already gave this to you, so classification of all harmonic polynomials into variables. Did you do this? Try it. So exercise, classify all harmonic polynomials in R2 yes.
I suspected that there are the coefficients, the real part,
yes,
the
this is a
imaginary part of
yes.
every polynomial, complex polynomial.
This at the end is true. At the end, but it requires somehow a little bit more. Why there is nothing else?
Mm-hmm.
This is the problem.
So
Classify harmonic polynomials, and the answer is that they are a linear combination. So if you take this, which is holomorphic, and therefore the real part and the imaginary part are harmonic, essentially they are generated. I mean, you can, first of all, you can see that you can reduce to homogeneous harmonic polynomial. So homogeneous meaning that you have, say, for instance, alpha x4 plus delta x3y plus gamma x squared y squared plus delta xy cubed plus gamma y squared. So first, the first argument is reduced to such. This is, for instance, is homogeneous of degree 4. Any polynomial, you can write it as a sum of homogeneous polynomial, which are not monomials, but are just homogeneous polynomial of a specific degree. You show that it's enough to classify harmonic homogeneous polynomials. So you can suppose this you have to show. So you can suppose that these are homogeneous. This polynomial is homogeneous. For an homogeneous polynomial, you should prove that linear
Translate conjugate, harmonic conjugate.
harmonic.
It's not necessary to go to
Maybe
that.
I don't think that it is really necessary to go to the conjugate harmonic polynomial. At the end, it's correct. You have to take into account the linear combination of the imaginary part of this plus and the real part of this plus and the imaginary part of this.
Sorry, what does it mean classify? There is some classes or something?
No, it is at the end, is what I was saying.
So,
First of all, that all homogeneous, that you can split it in the sum of homogeneous polynomial, any homogeneous polynomial of some degree must be a combination, linear combination of, and there is nothing else. This is the point.
okay. I think we did, for example, in complex, we did R2 is C1, just
Yes.
you can say C1, and so we did in C1 in first lecture just for example, every harmonic function there is a only unique holomorphic function, which is this real part, or there is a this theorem it's related.
You mean because the problem of conjugate harmonic?
Yes, conjugate harmonic and Riemann-Cauchy equations.
Supposing that you have
We have
simple
a harmonic
connectedness
function,
on a
so
simple connected domain,
yes.
and this is not uniquely determined. It's up to a purely imaginary constant. Okay, let's. But I think that you don't need that. I don't know.